Okay, let's finish off Chapter 7 review questions. We're moving on to dissipative interactions now. 22, a car collides totally inelastically with a parked car. Okay. In the isolated system made up of the two cars, is all the initial kinetic energy dissipated during the collision? What's the answer to this? What do you think? Well, remember this guy from Chapter 6. Remember that the total kinetic energy of the system is made up of two components. It's made up of the system kinetic energy, which is the kinetic energy of the center of mass. Okay, I can't go into teaching this all over again. Make sure that you understand this. And it's got this component, which is in another equation. This is your convertible kinetic energy, and that's your non-convertible kinetic energy. Okay, so remember, in an isolated system, this part cannot change. Your non-convertible kinetic energy cannot change. But your convertible kinetic energy can change. So this is the way to answer this question. It says here, okay, so it's totally inelastic, right? You got a car, and a parked car, and this car is moving, and then they crash, and they move together. Okay? So the first thing actually that I've often encountered with students is that the minute that they see totally inelastic, they think that the final kinetic energy is zero. Meaning that the minute they see totally inelastic, then there's no relative velocity. They think the total kinetic energy is zero, which is not true necessarily. Okay? If this guy's coming and it crashes into this guy, and they might still be moving. So there is a system kinetic energy that's still there, but we also have the convertible kinetic energy, which has changed. So the system kinetic energy has not changed, which is the non-convertible kinetic energy, but the convertible kinetic energy has changed. Okay? All right. So the answer to this is only the convertible part of the system's energy is converted. The inconvertible part remains as system kinetic energy. By the way, go check out section 6.7 in the textbook, 6.7, and specifically example 6.8. This will clear up everything. It shows this example here of a car crashing into another one, and then they move with a specific velocity, and then the other one is you've got two cars of equal inertia colliding and stopping. They stop. Okay, so the final velocity is zero. So in this case, all of your total final kinetic energy is zero. In this case, it's not. Okay, so go check that out. Make sure you check that out. Okay, so in this case, some final non-zero velocity, right? Non-zero velocity, and hence final non-zero kinetic energy is needed to keep the system's momentum constant. Okay, so please make sure that you understand these concepts. Okay, let's see. Let's just read through 23 and then I'm done with this. In a collision between two objects, how much of the convertible kinetic energy is converted to thermal energy? Okay? And how much is temporarily stored as potential energy during the collision when E equals 1 and E equals 0? So E equals 1 we know is a elastic collision, and E equals 0 is totally inelastic. Okay, so check out this equation, 726. It relates the change in kinetic energy to the change in thermal energy, okay, which is then equal to this equation here, half mu, and remember mu is your reduced inertia. Make sure that you go and check that out. Reduced inertia. Make sure you know what that is. V12I is your initial relative velocity, and then 1 minus your coefficient of restitution squared. Okay? So, if we use this equation, we can see that none of the convertible energy is converted to thermal energy, okay, if we have an elastic collision. Okay, so does this make sense? Elastic means you've got two objects, they go boom, and then they bounce off each other, and they start moving again in the opposite direction. Elastic means that the initial and the final relative velocities are the same, which means that it is a it is a reversible interaction. It is non-dissipative, okay? So, that means all of the convertible kinetic energy was temporarily converted to potential and then converted back to kinetic energy. Does that make sense? Okay? So, if we put a 1 there, if we put a 1 in there, this whole thing is 0. So your change in kinetic energy is 0. So there's no change in thermal energy. Okay? So your change in thermal energy is 0. Okay. Now B, what about a totally inelastic collision? There's a 0 there. This becomes 1. Or this becomes your delta K equals minus this, right? Yes, okay. So equation 726 tells us that all the convertible kinetic energy is ultimately converted to thermal energy. Right? All of it is ultimately converted to thermal energy. Does that make sense? So it crumples up. There's no potential energy. There's permanent deformation, and it is converted to thermal energy. But all or part of it may still be temporarily stored as potential energy, but ultimately converted to thermal energy.